All right, good morning, everybody. Welcome to Science Seminars. Okay, we have 2 more science seminars after this week. Next week, Henry Horace will be here to talk about batteries, using some system for batteries. I forget, so I'll have to check it out, find out. And then that'll be the 20th, and then 27th will be our last science seminar. It'll be something that's really out of this world. So you want to check that one out as well. Speaking of out of this world, today's science seminar is really out there, and it's going to be a massive seminar. I'm not sure if we'll be able to fit it all in the time allowed. Super massive it is, yes. We have with us today Krista Lynne Smith from Southern Methodist University over in Dallas. Dr. Smith grew up in the area here. In McKinney, wasn't it?
That's right.
Yep. She did her bachelor's of science. Was it in physics?
Astronomy. All of them are in astronomy.
Everything's in astronomy at UT Austin. Then she went and got her master's and her PhD from the University of Maryland, where she worked with the Goddard. Was that? Yeah, that's up there in Maryland. Yep. And then she did her postdoc at Stanford, where she was the what? The Einstein something fellow. She was an Einstein postdoctoral fellow. So young Einstein we have here, you could say. And then from there, she went to start her career in teaching at Southern Methodist University in 2020. So she's young in her career as a professor, and she is eager to do research, and she's looking for students that want to get their graduate degree in astrophysics, astronomy, and things like this. And she's going to tell you about the wonderful things that she does there. And then after the seminar, we'll be taking her to lunch, so you can join us for lunch in the Joyce Room, if you'd like, and ask her other questions about her life in the sciences and things like this. All right, so let's see if Dr. Smith.
So thank you so much for having me. I'm really excited to have this opportunity to come out here, see Latorno, meet all of you. And like was mentioned, we have a new track at SMU for we have a new track at SMU for graduate program in astrophysics or astrophysics and cosmology in the physics department. So I'm quite interested in students who are thinking about graduate school in astronomy or physics, cosmology, whatever. So do ask me about that. And we at SMU would love to build a relationship with Latorno if students here are interested. So today I'm going to tell you about my research, which concerns supermassive black holes, and I call my talk Through the Kaleidoscope, because understanding supermassive black holes actually requires that we look not only at all the different types of light, all the different colors that are emitted by black holes, and the light that the material surrounding them, but also how those relationships between those colors and different wavelengths of light change with time, just like in a kaleidoscope. So I wanted to begin with an overview of black holes in a physical sense for people who may not have thought about this for a while. So the way that we typically think about space-time is that it is a dimensional space that can be warped by mass. So what I'm showing up here is a two-dimensional metaphor for that. You can think of space-time as this sheet. Think of it like a surface of a trampoline. And what happens to space when you put something massive in it, like perhaps this is a star or a planet, it bends space around it. And objects have to move through space. So if space is bent, then another lighter object, like this blue ball, which you can think of as a moon around a planet or a planet around a star, follows that space-time warp. And that is what we think of as an orbit. So when something orbits something that is more massive, what it's really doing is following the curvature of space in the presence of that massive object. But a black hole is a much more severe warp in space-time. So you can imagine it like this bottom video here, where it's not a simple kind of well in space-time with a finite depth. It is actually an infinitely deep well with very severe curvature. And that is, in a physical sense, what we mean when we say a black hole in a mathematical sense. So there's multiple types of black holes. The first type is a stellar mass black hole. This is what happens when you have a large star that dies, a star that's larger than the sun. And those have masses of about 3 to a few tens of times the mass of the sun. And then there is a class called supermassive black holes. And these are much, much larger. Supermassive black holes have 10 to the 6 is a million to 10 to the 9 a billion times the mass of the sun. So there's a huge gap in between the masses of these stellar corpses and the masses of this supermassive population. Now, there is a class of intermediate mass black holes that is becoming more clear, becoming more common in different types of observations that I won't get into today, but there's only maybe a dozen or so candidates for intermediate mass black holes where we have many, many, many known stellar mass black holes and hundreds of millions of probable supermassive black holes. So how do these things form? Where do they come from? We think we understand the origin of stellar and intermediate mass black holes. As I said before, they're what happens when massive stars reach the end of their life. They exist, they're nuclear fuel, there's nothing to push back against gravity, and so they collapse into a black hole. Intermediate mass black holes are probably the products of mergers between stellar mass black holes. But we don't actually know the physical origin of supermassive black holes. It's one of the great mysteries of astrophysics. Not only how they form, but how they formed so early in the history of the universe. So, there we go. So what else do we know about these supermassive black holes? Well, we know where they live. So this is a picture of a barred spiral galaxy. This is the type of galaxy we think the Milky Way probably is, with this central stellar bar and these big arms. And we think that supermassive black holes live in the centers of every massive galaxy. Maybe every galaxy. That search is ongoing, but certainly every massive spiral like this, like the Milky Way, like Andromeda, large ellipticals have a supermassive black hole at the center, much, much smaller than the size of this black box on the screen. It's just there to kind of guide your eye. And the Milky Way is no exception. The Milky Way also has a supermassive black hole at the center, and in a couple months in the summertime, from Dallas, from this area, if you go out and you look to the south, you'll see this kind of fishhook shape. That's the constellation Scorpius, and this teapot shape, which is actually the Archer constellation Sagittarius. And in between those two constellations is a star called 3 Sagittarius, which is very close to the location of our galactic center, the location of the supermassive black hole in the center of the Milky Way. You can't see it because it's a black hole, but it's there. If it contents you to look towards it. So how do we know it's there? Well, the video that's playing on the right-hand side of the screen is showing an experiment carried out at Keck Observatory, and you'll see that the year is given up here in the top. And what you're watching happen as the time progresses is images of stars in the center of the Milky Way galaxy moving in orbits, and they're all orbiting something. But there's nothing there. There's no light at that location. You can't see anything there with your eyes where you can see these stellar orbits. And by using Kepler's laws of planetary motion, we can calculate the mass of whatever thing those are orbiting. The equations are not too complicated. And it turns out that something in that relatively small region has to weigh 4 million solar masses. And it has to be a black hole. It's there, it's small, it's giving off no light at all. And so this was actually the recipient of the 2020 Nobel Prize in Physics. The experiment I just showed you was run by the woman on the right, Andrea Ghez, and was the confirmation of the presence of a supermassive black hole at the center of the Milky Way. And so I said, they live at the center of every massive galaxy. And most of the time, like our Milky Way black hole, they're what we call quiescent. They're difficult to see, they're difficult to study, they're not giving off a lot of radiation. But about 10% of the time, that black hole is what we call active. That means it is consuming material, it's consuming a large amount of matter, and because it is doing that, it's generating a huge amount of light. The light's not coming out of the black hole. It's coming from the material that's falling into it. And that is what we call an active supermassive black hole, or an active galactic nucleus, plural nuclei. So the nucleus of that galaxy is active. Active galactic nuclei, or AGN. And AGN is the type of object that I study. So this slide just shows you a kind of zoomed in picture of what we think that looks like. The black hole's in the center here, and the material that is swirling down into it forms a disk, which we call the accretion disk, kind of like water swirling down the drain in a bathtub. We also have this kind of, this donut structure of dust that surrounds the accretion disk, which we call the dusty torus. It's kind of a fluffy, fat donut that surrounds the whole thing. And then we have these jets that are ejected by the ejected from the material that is really, really close to the black hole, where the magnetic fields become very twisted into these great long funnels, and some of the material that's going into the hole is sucked into those magnetic funnels and ejected. The black hole is not spitting anything out. A lot of popular science articles will say that, and they'll say it wrong. Something's spotted, flying out of a black hole. That doesn't happen. The black hole creates an intense magnetic environment because it is spinning and the disk is spinning, and stuff that's trying to fall into the black hole gets ejected instead. But much of the material does go down the hole. So this is my mostest favorite ever artist's conception of an active galactic nucleus. And you can see all the pieces we discussed: the accretion disk, the dusty torus, which is really beautifully visualized here, and this very well collimated laser-like jet being ejected from the center regions. Now, the important thing about this object is that each component radiates primarily in a different part of the electromagnetic spectrum. So the accretion disk primarily emits in the optical and ultraviolet. The very center regions of the disk primarily emit in X-rays. It's very hot. That material is a very hot thermal plasma. The dust out here absorbs that hot radiation from the center and reprocesses it, re-radiates it as infrared radiation. And the jet produces lots of types of emission, but is primarily studied in the radio and gamma rays. So we're spanning the whole electromagnetic spectrum from very long wavelength, low energy radio to very high energy, short wavelength gamma rays. And in order to study these objects then, we have to use lots of different tools. So to study optical and ultraviolet radiation, we can use ground-based telescopes like the DCT at Lowell Observatory. These are 3 telescopes that I use in my own work. The TESS Observatory, it's a timing instrument, and there's Hubble there. To study the X-rays, we have to go into space. X-rays don't penetrate the Earth's atmosphere. So we have XMM and SWIFT shown here, and this little thing is about the size of a washing machine. It's attached to the International Space Station called NICER, and I use that to do some X-ray studies of the jets of these AGN. We can study radio emission from the ground. This is the Karma array and the Very Large Array out in Socorro, New Mexico, which I had the privilege of walking all over in September after having used it for 15 years. I had seen it with my own eyes, which was really cool. With the infrared, we have a few options. The infrared emission doesn't reach all the way to sea level. It does get down into the Earth's atmosphere, but just not very far. So we can either build our infrared telescopes on the tops of very tall mountains, and that's the NASA IRTF facility on top of Mauna Kea in Hawaii. We can put a telescope in an airplane. So this is the infrared telescope called SOFIA, which flies in a plane to take its observations. Or we can go into space, and this is a picture of the Spitzer Infrared Space Telescope. And then finally, for gamma rays, we also have to go into space. Fortunately for us, gamma rays don't penetrate the Earth's atmosphere either, and that is an image of the Fermi Gamma Ray Telescope. So it's a multi-wavelength effort to understand these objects. But not only do AGN emit in all these different wave bands, they are also variable at all wavelengths. So they don't just emit at these wavelengths, the brightness of that emission changes with time. So this is what we call a light curve. A light curve is a plot of how bright something is on the y-axis and time on the x-axis. So this is one of the first light curves taken of an AGN, and you can see that it gets brighter, and then it gets dimmer. There's a bright flash. Then it kind of stays relatively dim for a long time. But we also see this variable emission in the radio. This is a radio light curve of the same object. The baseline here is very long. This is a 20-year baseline. And you can see the variability of this object in the radio is quite extreme. And we see the same type of thing in the X-rays, variability in the brightness. Not only are they, oops, it looks like there was a squishing of the format, but they're not only variable at all wavelengths, but they're variable at a huge range of time scales. So here is a light curve that I believe says 8 years. So you can see the variability here over the time scales of a few months. This light curve spans only 4 hours, so you can see rapid variability on the time scales of a few minutes. And this is not a light curve, obviously, it's an image, but it gives us the information that these objects are actually variable over millennia time scales. And that is because this object, this galaxy, is not an AGN. Its black hole is currently quiescent, but there is this cloud of gas over here that was ionized, so the electrons in that gas were kicked out of their atoms by the high energy radiation coming out of this galaxy when it was an AGN. And it has now continues to glow as those electrons recombine with those atoms and give off that radiation. So it's cooling down after being ionized by this object, and the distance here is 10,000 light years. So we know that that galaxy was creating this emission at least 10,000 years ago. So, okay, they're variable. That's cool. So what can we do with that information? So in order to tell you what I do with my own work here, I have to explain had to go a little bit off topic here and explain this spacecraft called Kepler. Kepler was launched to discover exoplanets. Kepler was not meant to do this black hole stuff. It was meant to look for planets orbiting other stars. So what it did was it watched a field of the sky, looks just like that. That's the constellation Cygnus, and this weird shape is the shape of the Kepler field. And unlike a telescope that you point at places, the Kepler telescope stared at that one location for 4 years straight without blinking. And what it was looking for was an eclipse of a planet passing in front of that other star. This is a very difficult signal to see, so they built something with really incredible precision to detect this light and make these light curves, very long baselines, and it took a data point every 30 minutes for 4 years without looking away. So the only drawback with Kepler is that, like I said, it only looked in this one location. You couldn't steer it. You couldn't point it anywhere else. There is another visualization of the Kepler field of view on the sky to give you a sense. There's the Milky Way here. And Kepler was extremely successful at its primary mission, which was to discover exoplanets. On the left, I'm showing you a plot of the mass of known exoplanets in multiples of the Earth mass versus the orbital period in days. So the Earth is here, and our orbital period is like 300 days, so we'd be about here on the plot. And on the right is the same plot after Kepler ran for 4 years. So you can see how many Earth-like or similar planets Kepler discovered that we didn't know about before. So shout out to Kepler for being great at what it was meant to do, but it's also really good at stuff it wasn't meant to do. Now that limited field of view was a little problem for us because it was in our galaxy, looking for planets in our own galaxy, but we wanted to look at other galaxies with active black holes. So the first thing I had to do when I was a PhD student at the University of Maryland was conduct an X-ray survey of this field of view using the SWIFT satellite to look for AGN, to look for that X-ray emission from the hot inner part of the accretion disk. And here is a zoom in of the sky, the Kepler field of view, and here's the little points that we found in our X-ray survey that are likely to be active galaxies. And after we found the galaxies in the Kepler field of view, we were able to take these light curves. And you can see this is days on this axis. So this is 3 years of data, a data point every half hour for 3 years of this accreting black hole. Very rapid variability, stochastic variability. In this middle one, if we had only looked for 200 days, we wouldn't have seen anything. We would have thought it was not varying. But then some kind of an event occurs, some kind of perturbation in the accretion disk. And then we saw some objects that have both kind of things going on. Rapid variability, but also larger, more discrete, longer-term events. And what this taught us was that accretion disks are turbulent. We can model many of these variations with turbulence. They're viscous, the viscous timescale, and most of that viscosity is magnetic. So there's magnetic loops, magnetic reconnections, magnetic flares, viscosity due to the magnetism, and they're very dynamic. The disks are not stately, steady state, accretion into the hole without any trouble. They give us a lot of information about the behavior of matter in these high energy environments. But Kepler, I won't say that it died. It retired gracefully after being very successful in 2018. So to keep going, NASA was not satisfied with the bazillion new exoplanets and decided it needed a gajillion or something. And so what it did was built the Transiting Exoplanet Survey Satellite, or TESS, which is the successor to Kepler, pictured here. It does something very similar. It does that thing where it looks and it collects a light curve with very fast cadence, 10-minute cadence. The baselines are shorter, so it only does it for about a month, 27 days, up to a year, depending on where you are in the sky. But importantly, and this is a map here of the length of the TESS baseline, the length that it looks for. So most of the sky has 27-day baselines, and then these wedges that overlap have a little longer, and then eventually at the ecliptic poles you have a full year of monitoring, and the video on the next slide will show you why that is. So the advantage is that it's nearly all sky. This is repeated on the other hemisphere. So instead of that one little field of view, which didn't overlap with a bunch of known AGN, the entire sky is being surveyed by TESS. So that really makes a big difference. So this video will show you. Oops, sorry. I thought it was broken.
Megapixel sensor covering a 24-degree square, large enough to contain an entire constellation. TESS has 4 of these cameras arranged to view a vertical strip of the sky called an observation sector.
The coverage of the TESS cameras.
And then we don't want to let George Ricker talk. Yeah, okay. So
I guess they fixed the audio.
I guess so. I would have removed that. I would have removed it otherwise. So TESS observes in these big wedges of the sky, and then it moves every month to a new wedge, but they overlap at that top camera, which is why you get a full year in each hemisphere at the poles. Okay, so that's accretion disks. The next thing I wanted to tell you about that involves the variability of these objects is binary supermassive black holes. So we know that galaxies merge all the time. We can see in Hubble images galaxy pairs, or even more than pairs, at different stages of these mergers where the galaxies are brought together by gravity, interact, and then eventually form a remnant galaxy. And I've already told you that all galaxies have a supermassive black hole at the center. So it stands to reason that at the end point of this galaxy merger, you would end up with 2 of these huge things trying to merge together themselves. This is a computer simulation image of what we think happens there. So late in the merger, once the galaxies have mostly finished merging together, the black holes are in close proximity. There's a big accretion disk, what we call the circumbinary disk, and then there's a gap that is hollowed out by the orbit of the merging holes, and each hole is surrounded by its own accretion disk within that gap, and that accretion disk is fed through streamers from the circumbinary disk. Now, these are orbiting each other. These things are going round and round. And so we might expect in a light curve to see periodicity in this case, to see an oscillation. because as the black holes go round and round, the streamers that are feeding them will bang into each other, causing a flash of light. And we just expect that the orbit itself, even without that flash of light, would produce a periodicity because of how the motion of those black holes boosts the emission as it's moving towards us and diminishes it as it's moving away. So people have looked, people have attempted to find candidate binary black holes in merged galaxies by taking light curves and looking for a periodic signal. And this is kind of hard to do. So if you're looking at this and you're like, not thinking that's that periodic, it's kind of a generous interpretation of the data, you're not the only one. This is a difficult experiment because if you think back to those light curves I showed you a second ago from Kepler, there were things that looked periodic in that light curve, but then it would go and do something else for a while. And that was not because it's a binary, that was because of random kind of dynamic motions in the disk. So it's hard to tell if what you're seeing is really a binary just from the fact that it kind of looks oscillatory. So we want to do this better. There is a more specific phenomenon that can help us look for binaries in these periodic objects more precisely, and that's utilizing gravitational lensing. So remember our visualization of space-time as the sheet of rubber. This massive object is moving through space, and it passes along our line of sight to a background source of light. When it's in the way, the light from the background source has to bend around the object, which increases it almost makes it look like there's multiple images. It does make it look like there's multiple images of that background source. So the light curve, which is shown here on the bottom right, gets brighter and then fainter as the lensing source moves, or the lens, which is the little red ball, moves out of the way of the background source. So, in 2018, I saw a talk by Dan D'Orazio, who's a theorist at Harvard, and I stopped him after the talk because I was so interested in this signal. And here is the theoretical prediction of the signal from so you have the regular periodicity. That's just the periodicity from the orbit from the merger. But at some point in that merger, in that period, there's a flash from the self-lensing flare. When here's a person's eyeball here, and here's the foreground black hole. When this black hole with this accretion disk passes behind it in a very particular geometry, we can see this flash, and then it moves out of the way and goes on about the orbit, and then it happens again and happens again. And I approached Dan about this because I had this weird thing in my Kepler sample, which I had been trying to make sense of for months, where there is, this kind of trend of the light curve that isn't very special, but then there's this bright flash. And we called this thing spiky, and the journal let us get away with it, so it's in the paper. I think it's even in the title of the paper. And if you model my light curve, which is the black points, with the possible model for the lensing flare, you can see in this zoomed out and in the zoom in of the flare itself that the model is quite a good fit. So this is a candidate object for a binary supermassive black hole. And we are continuing to watch this because one of the great things about a periodic signal is that it should keep happening. So hopefully in the next couple of years we will see a repeat of this, and then we will be able to confirm that this object is indeed a binary candidate. So for the final part of the talk, I'm going to tell you not about variability, but we're going to zoom out a little bit, and we're going to think about how these very energetic objects interact with their host galaxies. So we've been talking about this, what we call the central engine all this time, the black hole itself, the material that's falling into it, the magnetic fields. But what about the galaxy that thing is sitting in? So this is a very beautiful image of a zoom in of the Hubble Deep Field, which is showing galaxies. Everything in this image is a galaxy except things that look spiky like this, which are stars. And there's only, I think, one star in the whole image. So these are all different types of galaxies. And what I want you to notice is the diversity. So big orange round galaxies, little blue disky galaxies, all the colors, all the shapes. All of them galaxies like the Milky Way. And it turns out that in order to understand why all these different colors and shapes exist, you have to have an active black hole in the center of the galaxy. So why? In order to answer that question, I work with a group called the BAT-AGN Spectroscopic Survey, or BASS, which is a multi-wavelength survey from radios to gamma rays of X-ray selected AGN in the sky using an instrument called the BAT on the Swift telescope. And what I do is the radio imaging part of this. So there's optical and infrared spectroscopy, there's X-ray spectroscopy, there's optical imaging. So people on the team do all of these things, but my part of this is to do radio imaging of these AGN in these host galaxies. So what I have done is I've used the VLA, pictured up here. It's in the movie Contact. Have you ever seen the movie Contact? Great movie. And I use the VLA to take radio images of these AGN host galaxies. And the properties of my survey, it's at 22 gigahertz, if anyone's a radio person in the room. 1 arc-second resolution, so that's very good resolution in the radio. That means we can see small structures. And what we see is these different shapes of the radio emission. So kind of blobby shape here, a kind of shape that looks like it has an outflow maybe in these two directions, and objects that have what looks like this jet. So remember that I said the jet emits in the radio? This jet-like shape, but also has some fainter emission. We know that regions where stars are forming can give off radio emission also, which is probably what's happening in this image. We detect 96% of the galaxies that we image in this radio survey. So that means that even the faint, small AGN that we're studying, not these big, super bright quasars, give off radio emission in some form. This is some work being done by my graduate student, Macon Magno at SMU, who is using our 22 gigahertz data, but is combining it with images at all these different frequencies, using lots and lots of different radio telescopes. And he is, so stay tuned for this work, where he's building up kind of the radio information, not just from the VLA, but he's also going to Australia this summer to work on the GLEAM-X array. These are the kind of opportunities at SMU. Go to Australia. You love it. So what do I mean here when I say that we can study how these host galaxies are affected? So it turns out if you make a plot of all the galaxies, just all of the galaxies, and you have one axis that's the color, so blue on the bottom, red on the top, and one axis that's the mass, low mass to high mass. If you make that plot, these contours show you where all the galaxies fall. There's a bunch of low mass blue ones, which we think look like these star-forming spirals here. Young stars are blue. So when you have a lot of star formation going on, you have a lot of blue stars, like in this one, so you're down here. And then up here in the top is a bunch of big, massive red galaxies, like this elliptical. And so the stars all get formed, and the galaxy becomes massive. And once you're out of fuel to form new stars, you have only red stars, old stars. Young stars that are blue, they die really fast. And so if you have a red galaxy, all the stars are old, not very many new stars are being born. But if you plot up on the same plot only the host galaxies of AGN, remember only 10% of galaxies have an active black hole. Okay? If you plot all of those up, they all lie in the middle here, this region that we call the green valley, in between the blue cloud and the red sequence. So this is usually a place where you don't see very many galaxies. Most of them are in these big blobs. But if you put only AGN host galaxies, galaxies with an active black hole on the plot, they all fall in this middle region, or not all, most of them fall in this middle region. And so the question is the AGN somehow helping the galaxy transition from a blue star-forming galaxy to what we call a red and dead elliptical? And we call the process by which the AGN may affect the galaxy AGN feedback. Now this can happen two ways. This is now a simulation, supercomputer simulation, where the color denotes the density. So low density is red and high density is blue and purple. That means it's colder gas, low density gas. This is a simulation of the whole galaxy disk, not the AGN accretion disk, the entire galaxy. So the black hole's in the middle. It's ejecting very hot gas along the jets here. But it's doing a couple of things in this image. There's two ways you can stop the star formation. You could either just kick the gas straight out of the galaxy, If there's no gas in the galaxy, you can't form stars from it because it's not there. Or you can heat the gas. See how the jet is actually contributing energy and making the density lower in the inner regions of the galaxy? You can heat the gas, and the hot gas will not collapse. It'll support itself against its own gravity, and you have to collapse gas to form stars. So both of these things that the AGN jet is causing can reduce star formation. And in my own work, here are some optical images, just normal visible light images in red, with the radio image from the VLA in blue on top of them. These are relatively little jets, right? They're not, this one's kind of big, but this one's teeny weeny. This one's pretty small compared to the entire host galaxy. But what I find is that even AGN with these modest outflows are significantly affecting the star formation in the host. So this is a plot of the rate of star formation in the galaxy, in a galaxy, versus the galaxy's mass. And all the little gray dots are non-active galaxies, just normal galaxies without an AGN. And all the triangle colors are galaxies from this sample that have these tiny little jets. And you can see that they have a lower on the y-axis rate of star formation per unit of stellar mass than their cohorts, which are inactive. So even when it's not super powerful, these jets have the ability to transition galaxies from blue and star forming to red and dead. Oops. And the last AGN slide is to show some work by my undergraduate, Andrea Reyes, who uses the MUSE telescope in Chile to study the behavior of the gas, the ionized gas. So in this image, the green is the radio contours, and the colored image is oxygen-3 emission, so emission from ionized oxygen gas, that you can see is tracing the radio, which shows us that the emission from the AGN is actually ionizing this gas. We can also see how it pushes the gas around and changes its velocity. And so this is a really cool program that we've just gotten the time on this past summer. And finally, TESS is fun for lots of things, not just AGN. It can also, and not just planets. It can do high energy astrophysics of stellar objects. So when a really, really big star dies, there's a huge explosion called a gamma ray burst. And TESS actually saw one, and because there aren't that many people doing high-energy astrophysics with TESS, it somehow fell to me to write this paper. So you can see the TESS light curve here. This dashed line shows where a gamma-ray telescope, Fermi, saw the gamma-ray flash occur, and then you can see there is a spike in the TESS light curve. Here is the image before it, and look. Ooh. You can barely see it, but it's there. A new source at the location of the gamma ray burst. So TESS is now, because we know it can do it, looking for some of these very high mass stellar explosions as well. So in this talk, you probably have hopefully learned that supermassive black holes live in the centers of almost all galaxies and have a profound effect on the evolution and appearance of those galaxies and therefore of the universe in general. And we, as a species, must use all our resources around the world, in space, whole electromagnetic spectrum, over time, to understand these powerful and mysterious objects. And with that, I thank you for your attention and happy to take your questions.
All right. Woo! Time to wake up. I thought it was better with the lights out to see.
Well, there's lots of pretty pictures.
Yeah, this had a lot of pretty pictures. So you guys can give me your feedback afterwards, whether you want lights on or lights off. Time to wake up wherever you are. There's questions for our speaker today.
There's one over here.
Okay, go ahead.
If you go back a slide, there's something interesting in the graph I'm going to ask about.
This one?
Yeah, so the white graph on the top right, I'm seeing that some of the data values are below 0. Could you explain that?
Are they below 0? So it's very close, yeah. So it would probably, okay. What you're touching on is that the pipeline that I use is imperfect because one step you have to make in the pipeline is subtracting the background. And so in the image, there's not, well, over here it's easier to see. It's not just totally black. Oh.
It won't point on there.
Oh.
You have to do the center.
I love it.
You have to use the screens.
Okay. Anyway, so it's purple in the background, not black. So there is some background flux in the image. And there's a lot of scattered light and other trends that happen in the background that affect the light curve. So one step you have to take is to subtract the background trend from the light curve before you can see it. And if you don't do that perfectly, then you over subtract on some data points, and they would end up close to or below 0 in that case. So, yeah, it's a good catch. Yes.
I guess so. So this is a bigger, more general question. We know that black holes exist. So what?
Yeah. So fundamental research has a long history of being useful, much later than you think it will be. So, for example, black holes are a consequence of general relativity. General relativity was dreamed up in 1916 through 1919 by Albert Einstein. The curvature of space, that's what general relativity describes. And in that time, people asked very much the same thing. So what? So space is curved in the presence of massive objects. Okay, I have to drive to work and pick up my paycheck and, whatever. But today, we wouldn't be able to use GPS without understanding it, because the satellites that orbit the Earth are in the space-time well of the planet and would actually be off by about 10 miles if you didn't account for relativity in the calculations from the satellites. Quantum mechanics is similar. So what if the particles are made up of quarks which vibrate with some frequency? Well, we wouldn't be having, this only runs because we understand quantum mechanics, right? So black holes provide for us a laboratory we can't replicate on the Earth. We can't bend space that severely in a laboratory. We can't study the behavior of material in that kind of region that way. So all we can do is look at these laboratories nature gives us with all the tools we have to try and understand fundamental physics given the observational probes we've got.
Okay, so then you're trying to observe the I guess astrophysics and make predictions based on what you know.
Yeah.
You know currently.
Exactly. So we're trying to understand whether our current perception of general relativity and way space behaves is consistent with the astrophysical observations.
Okay.
Yeah.
Other questions for our speakers? We've got a few minutes, yeah.
Another one. Okay.
You said you were working out in New Mexico in the radio wave farm, whatever that was.
The very large array. Yeah.
Yeah. What's it like day to day, just looking for radio waves? Is it like a consistent thing, or is it like?
Yeah, so there's two ways to do it. There's sort of the traditional observing way, which is that you write a proposal to get time on the instrument. If it's approved, you go out to the instrument and you plan your observations and you stay out there and collect the data, and then you spend the rest of the time sleeping or reducing the data and then planning your observations for the following day. It's a lot of thinking on your feet because weather or atmospheric disturbances or what we call radio frequency interference from airplanes can ruin an observation, so you have to kind of redo it. But the other one is called Q observing, which is where you schedule your observation. You give them the coordinates of your source, and the machine decides how to slot everyone's approved observations in the most efficient manner. And so the VLA usually does that automatically, which is a bummer, because that's why I had not seen it until last year when I actually went out there to do it. But a lot of the ground-based traditional observatories still do it the old-fashioned way, which is less efficient technically, but is kind of fun.
Okay, questions from other people in the audience?
Yes.
There's Josiah over there.
Oh, Josiah Baker, have a question?
I'm forgetting the name of the satellite, but the one I was supposed to look at exoplanets, but I also ended up looking at the active black holes.
Kepler or TESS? Kepler was the first one.
The first one.
Okay, Kepler. Yeah.
One thing I noticed that the one slide that you had that had all the spots where there have been noted black holes, it looked like they were all in the ecliptic plane.
Well, okay, so yes, they are all in the ecliptic plane. So Kepler chose its observing to be in the ecliptic plane because it's slightly above the galactic plane. It would be too crowded if it was in the galactic plane, but it's still in the Milky Way. But you're right, those observations that I showed were all in 4 linear modules of the Kepler field of view. And that's because the Swift satellite only gave us like 1 million seconds or something. So we had to choose which region of the Kepler field to survey. And those were and doing it in a line was the most efficient way to kind of go in a grid pattern with the X-ray telescope over that region of the sky.
Okay.
If they would have let us, we would have done the whole thing, but, you know,
Okay.
other people want to use a telescope.
Any other question? Oh, there's one over there.
Oh, yeah.
And a bunch of your slides regarding the Kepler field is kind of in that weird shape and divided, like those funny little rectangles. Is there a certain reason you have it divided up that way?
Yeah, so NASA designs that because each one of those squares is 2 CCDs, charge coupled devices. So they're chips that are arranged to cover the sky. So the light has to fall on the silicon of those chips. So the reason it looks like that on the sky is because the actual instrument, which is like this big, looks like this, because you built it out of those chips. So when you take that and point it at the sky, it has that funky shape. And that shape probably is because you had to fit a certain number of chips in a round, you know, metal apparatus to put in the spacecraft, and the spacecraft can only be so big. But it's a good question, yeah.
This is more about black holes in general, which I've not gotten a satisfactory answer before. It's the idea where if no information can travel in or out of a black hole, what would happen if all the mass inside the black hole instantly vanishes? Would the gravity field still continue because the information that the mass disappeared can never leak out?
So the gravity field, you're saying if the mass all disappeared?
Yes.
Well, I think the problem with the question is that it can't. Because in order for the mass to disappear, it has to leave the black hole. So maybe it's a chicken and the egg question. I mean, you've probably heard like if the sun vanished, that a few minutes later, 8 minutes later or something, that the solar system would sort of disperse. If you snapped your fingers and changed the singularity of the black hole and destroyed it somehow, magically, then yeah, the gravity field there should be no bend in space-time anymore. But the problem is that, how is that going to happen? I mean, how can you get rid of all the mass in the black hole?
Well, I'm more of asking, how would the surrounding universe know that the mass inside the singularity disappeared when that information could not propagate outwards because of the singularity in the first place? It would seem to me that if you deleted all the atoms inside the bubble, the outside can't see in and see it disappeared, so you would keep falling into something that's not there anymore.
But the material inside of it does know about it. So the inside of the black hole isn't just, there's an event horizon, there's nothing in it. The inside of the black hole continues to have space-time curvature all the way to the singularity. The singularity is the infinitesimal point, and the event horizon has a finite size around it. So you can have things happen inside the black hole, but the universe outside can't know about it. I think and you're not wrong, the logical reasoning in black hole astrophysics is crazy. It's because causality breaks down when you exceed the speed of light, and the speed of light can't travel. The problem is, with the supposition of the question, that if you delete, as you say, all the atoms in the black hole, they have to go somewhere. And so in some way, just asking the question means that you're assuming that it communicates with the outside universe. They can't just go nowhere. But this kind of logical looping is not uncommon in these kinds of questions. But I think are we busting up against that? You said.
Yeah, that's probably a good place to close up. If you've got more questions, you can come down and ask them. And you can also meet us over in the Joyce Room of the Corner Cafe for lunch. Let's thank our speaker one more time.